You're going to be using the mic?
Yeah, I'm going to be using this one.
Oh, you're going to hold it. Okay, can you just tell us a joke or something? Okay.
You guys ready? Good. All right, well, good morning and welcome to my talk. Today we're going to be talking about using reverse engineering to uncover vulnerabilities or mobile risks in iOS applications. So a little bit about me. My name is Patrick Wardle. I've worked at a bunch of acronym places. Currently, I'm the director of R&D at Synac. Synac is a crowdsourced vulnerability discovery program. We use vetted security researchers. We have an internal R&D group, and we're backed currently by Google. We also do a lot of kind of cool cybersecurity research. We've released some open source tools. So just briefly want to mention what Synac does, the business model, in case any of you guys are interested. Basically, anyone can sign up. There's a vetting process, just to make sure you kind of know what you're doing. And then basically get paid to find bugs. So our customers come to us with mobile apps, websites, IoT devices, and they say, hey, we want to see if this is secure. So our external researchers who are signed up basically hack on these devices, websites, whatever, and anything they find, they get paid out. So it's a pretty cool business model. Customers love it. A lot of times their security is really bad, so our researchers love it as well. Get paid out. So this is something that's interesting to you. Definitely check out Synac. Kind of cool business there. All right, so today we're going to learn how to reverse engineer iOS apps with a focus on finding security and privacy vulnerabilities. So what I'm going to be talking about today, we're going to start off with a brief technical overview of the environment that iOS apps execute within. We're then going to be talking about getting the right tools for the job and then how to prepare iOS apps for analysis. For example, they're encrypted, so before you can reverse engineer and analyze them, you have to decrypt them. Then I'm going to talk about some iOS-specific methods of reverse engineering. It's kind of a unique platform, so there's some certain tools or tips and tricks to use. And then finally, this is my favorite part, we're going to talk about some common classes of vulnerabilities that affect a wide range of iOS applications, and then actually look at some real iOS apps that either still are or were vulnerable. All right, so before we dive into all this reversing stuff, let's talk a little bit about Apple devices, iOS applications, and then some other general thoughts. So those of us who have Apple devices, we love them, and we put all sorts of private information on them. Just think about what's on your mobile phone. You got emails, you got photos, sometimes incriminating ones. You have banking stuff, a lot of mobile banking now. And then also your current locations, or geolocation stuff. I saw one interesting study that said that given all the information that's on these devices, these are actually now our most valuable devices, and if someone were to access them or lose it and got stolen, this would be very problematic. And that's really the main problem, is since these devices are with us, we carry them when we go out to the bar, they're kind of small, we end up losing them all the time, or they get stolen. So there was an FCC study that showed that in major US cities, up to a third of all robberies actually were thefts of phones or tablets. And of these, 50% or so had no passcode lock. This is really problematic because it means even the most unsophisticated attacker can just boot the phone and then access all the sensitive information that's on it. So I'm really paranoid. I sleep with my phone under my pillow, so I'm like, oh, I'm good, right? No one's gonna steal my phone. Well, it turns out that even when a phone is in your possession, your data may not be safe. And this is because of buggy apps, and this is pretty much what we're gonna be talking about today. So apps may transmit sensitive data insecurely, which is problematic if there's a network-based attacker. They also have large, often untested attack surfaces, so that are processing a lot of data from other users or from potentially malicious sources. So they could be vulnerable to exploitation. Another problem, not so much on iOS, it's more of an Android thing, but even still on iOS, most apps are closed source, which means they could contain shady or malicious logic. You don't see a lot of malware in the App Store, but there's some apps that might be exfiltrating your address book or stealing your photo of your stuff. So, insecure apps there. And then finally, a lot of apps, if they don't secure their data safely and a backup is made, this ends up on a PC, which in my opinion is way easier to hack, even if it's a Mac or a Windows-based computer. So if an attacker accesses your computer and then you have this backup with all the sensitive information, they can access that as well. So you might be thinking, hey, it's 2015, talking about how important it is to write secure software, so secure apps should be the norm, right? Well, unfortunately, more often than not, apps are kind of buggy. So on the left here, we have some banking apps, some studies that were done that show the majority of these banking apps have some sort of issues. Citibank had a pretty bad bug. Social media apps, Facebook was storing credit securely. Tinder allowed its users to be tracked. And then even apps like Starbucks, had vulnerabilities which basically put its users at risk. So the reality is, iOS apps are pretty much insecure. So, what can we do about it? Well, it turns out reverse engineering, in my opinion, can definitely help. And, why can it help? Well, first, it can reveal vulnerabilities, which is always a good thing. On the last slide, those vulnerabilities I mentioned weren't found by the companies. They were found by third-party people who decided to reverse engineer the apps. It also allows you to verify the app. Is that Tor browser you downloaded from the App Store really a Tor browser, or is it something more malicious or shady? Reverse engineering can also increase security awareness. If you find a bug, hopefully you report it to the company. They should patch it. If they don't, you can talk about it at a conference, gives the company bad press. But the end result is hopefully the company improves the security of their devices and patches their application. And then if you sign up as a Synack researcher, you can actually get paid to find this kind of stuff. So that's always my favorite. So let's talk a little bit about the iOS environment, because I think it's important to understand some of the basics of Apple's operating system. We'll talk about the language of iOS apps, the CPU and the CPU architecture. So iOS is obviously Apple's mobile operating system. It's based on OS X or OS X, but it does have some extra security enhancements, obviously some touchscreen specific stuff, and then some mobile specific features. Now, this extra security basically has one goal, and that's to ensure that only Apple-approved code is allowed to run on the device. So some of these extra security features include a secure boot chain, there's signed code requirements, anti-exploitation mechanisms are built in, there's encrypted storage, and then apps are also sandboxed as well. So this actually locks down the device pretty well, which is good, prevents malware and a lot of attacks. For reverse engineering, or if you want to do your own analysis, these get in the way. So you pretty much have to jailbreak the device if you want to do reverse engineering on the device. So for the rest of the talk, when I'm talking about doing analysis on a device, just assume I'm talking about a jailbroken iPhone. So let's look a little deeper at the constructs of iOS application security. So again, the goal here is to only allow Apple-approved code to run, but also that to prevent apps from doing anything malicious. So again, this is going to be third-party code that Apple has tested in the App Store, but they want to make sure that even when it's running on the device, it's highly constrained. So the sandbox limits apps in a variety of ways. First, it doesn't allow any dynamic code generation, so an app can't call out to a web server, download some shellcode or payload it on it. The sandbox also gives no access to other apps' processes, so an application cannot inject itself into another app and gain access to its sensitive material. It also can't directly access the hardware devices. This is a good thing. For example, if your app wants to access your microphone or a camera, it can't directly do that. It has to go through an API, which allows iOS to pop up alert to the user and say, hey, do you want to confirm or not? And then lastly, apps are combined to basically the application directory they're installed in. They see this actually as the root directory of the file system. So it's kind of like a file system jail for the application. And again, end result, even if an app is misbehaving, it's very limited to what it can do. All right, so let's look at an app. So apps are distributed as .ipa files. I'm actually not sure what that means, that acronym. There's some suggestions on Wikipedia, but basically it's just a zip file. If you change the extension to .zip, you can double click it and it'll expand. It expands into this application bundle, which is really just an Apple term for a directory. This bundle contains all the app's files. So if you double click on this folder and look at it, you'll see the app's binary, images, metadata, and more. Pretty much everything the app needs to execute. So for reverse engineering, it's important to understand the on-disk layout of an application. Pretty much how it looks once it's installed on the device. Luckily, apps have a standard on-disk layout. Non-Apple apps are installed to the private var mobile applications directory. And then each application gets this unique UUID, just generated at runtime by iOS. So as you can see, this is how an app looks. This is the Bank of Hawaii app. If you do an ls or a tree command, you can see the application bundle, and then a bunch of other folders. We'll be talking more about the library folder because there's persistent data, application settings, and sometimes contains sensitive information. If you look at the actual app folder or bundle, you can see things like the app's binary, config files, digital signatures, stuff like that. So apps, as I mentioned, are distributed as these IPA files that contain a single application and a single application binary. So you may be wondering, how is this single application bundle able to run on both older 32-bit CPU architectures like the iPhone 3GS, as well as the same newer 64-bit ones? And the answer is the binary is FAT. It's an Apple term. So FAT binaries are the standard format for Apple binaries. They're called FAT because they contain multiple architecture-specific binary images. Basically, you can think of them as an executable zip file that contains just multiple architecture-specific binaries. So if you look at the Apple source code for this, basically, how does a FAT binary look? How is it treated? You can see that it starts with this structure called FAT header. There's a magic identifier, which just tells the OS, hey, I'm a FAT binary. And then it has the number of architectures that are in this package. Immediately following the FAT header are these FAT arch structures, and there's one for each architecture that's supported. They have a CPU type and CPU subtype, so this would be like 64-bit, 32-bit, and then an offset into the package where the application binary is. So what happens is at load time, the loader parses this, and the loader knows what CPU it's executing on, and it basically then goes and finds the correct architecture. So if it's a 32-bit one, it's going to choose a 32-bit architecture, 64-bit, 64-bit. And the result, you pretty much just need one binary that will run on all devices. All right, let's take a closer look now at these architecture-specific binaries. So on iOS and OS X, this is a file format that's called mock-O. Now, mock-O starts with a file header called the mock header. This has, again, the CPU type and subtype. And then it has these number of commands and size of commands and some other flags. So these commands are important. They're called load commands. And pretty much what they do is they tell the loader how to set up the binary in memory. That's the right contacts and stuff like that. Following that then, so after the load commands, it's just the raw data, which is the binary code, text segment, code segments. This is actually what gets executed. So in reverse engineering binary, it's always important to know what language it was written in, what high-level language, because this allows you to understand kind of how it works, figure out APIs and stuff like that. So in Objective-C is kind of the de facto language for writing iOS applications. Swift was recently introduced, but Objective-C is still the most common. Now, Objective-C is basically C programming language, but it does have some object-oriented capabilities that Apple kind of bolted on. And then also, if you look at the syntax, it's a little weird. It's got like this at symbol and funky stuff. But it's pretty much just object-oriented C. So, as mentioned, the syntax is a little odd. If you look at the top left here, you can see some C++ and then some Objective-C. This is the same code logically. In Objective-C, though, it's all about passing messages. So in C++, you invoke a function to do something. In C++, what you do is you pass a message to an object with the name of the function you want to execute. And the object will receive that and then execute that. So it's a message passing architecture. At the bottom we have this Objective-C definition. It's got a lot of different parts to it and some funky syntax. Reverse engineering, you really don't need to understand all of this, but the one thing that's important to know is that this string gets inserted into the binary. So when you're reverse engineering, this is actually really helpful because what you can do is you can find method names and stuff like that and cross-reference them and figure out what's going on in the binary. So reversing Objective-C statically is kind of challenging. It's an object-oriented language, which means things are dynamically generated. And the other thing that's interesting is you see this call to obj-c message send all the time. And you might be wondering, what is this? Well, it turns out that whenever you write Objective-C code, source code, when you click compile, the compiler will generate a code that changes the call to go through this obj message string. So here we can see we have our C, Objective-C code, and the compiler then converts this into a call to obj-C message string. Now this function is documented by Apple, and so here's the dump from Apple docs. Basically, the most important things are the first two arguments. The first one is called self, and this is a pointer to the instance of the class. Basically, this is the class that's going to receive the message. Then the second parameter is a selector, which is just a fancy name for a name. And this is the method or the function that you're trying to invoke. So we'll look at some reverse engineering examples, but a lot of times what you do is you'll see a call to the obj-C message function. And what you do is you look back into this assembly because you're trying to figure out what is the object and what is the method that you're invoking. And then once you see this information, you can kind of tell what the application is doing.
Is this kind of like the vtable for?
Yeah, very similar. Okay. This is how it resolves.
Okay, but for cases in which the compiler was smart enough to statically figure out the target, does it still do this or does it optimize away?
It still puts us in. It's all just message passing, so it's just going to send the object a message. So it's actually more flexible than vtables because it's not compiled in like statically, like offsets and stuff don't matter. But exactly, it's basically how Objective-C does its object-oriented method invocation. All right, so let's talk a little bit about ARM. All iOS devices run on processors based on ARM architecture. So ARM, a little different than Intel. So it's a RISC-based CPU strategy, which means there's fixed instruction lengths. It's a load store architecture. This means that operands have to be loaded into registers before they're operated on and then stored back into memory. So there's no direct manipulation of data in memory. It's also encoded into various modes. So the first one is called ARM. This has a 4-byte instruction length. And then ARM, the company, came out with thumb encoding, which is a 2-byte instruction length. So this is beneficial because basically you can get more data in smaller space. Again, ARM is used in embedded devices. So it's a subset of ARM instructions encoded in 2 bytes. The final and most recent encoding scheme is called thumb2. It's kind of the best of both worlds. Instructions can be 2 and 4 bytes in length. So it generally achieves the same code density as thumb, but has the same performance as well. So ARM32 is the unofficial term for ARM architecture on 32-bit CPUs, so older devices such as the iPhone 3GS. So when reverse engineering ARM binaries, it's good to understand what the registers are, and their common names and stuff like that. So in terms of inside a function, R13 is going to be the stack pointer, where R0 through R12 are just general registers that can be used for whatever. R14 is the link register. And then R15 is the program counter, and then there's also the CPSR, which is just the program status. In terms of a function call, R0 through R3 is going to have the arguments. And then the return value from the function is going to be in R0 or R1. So when you're reverse engineering, you want to see the value that the function is returning, you just look at what's in the R0 position. ARM64 is Apple's term for the ARM architecture on 64-bit CPUs. So this is from the iPhone 5S and newer. There are some new registers and more of them. We can see X29 is the frame register, X30 is the link register, and then there's actually a dedicated named stack pointer and program counter. When you're making a function call, the arguments are going to be in X0 through X7, and then these are also going to be the return values, although generally just X0 is used. It's a good article by Mike Nash if you want to get kind of into the down into the details about all this. All right, so hopefully now we have a pretty good understanding of the iOS environment. So I want to talk about some reverse engineering tools and then how to also get and prepare applications for reverse engineering. So the good news is there's a lot of tools that you can use when reverse engineering iOS applications. And I've kind of split them into 3 groups. Over on the left, or the right, I guess, you can see a group of tools. These are pretty much just Linux tools that have been ported to iOS. So things like SSH, GEB, yeah, pretty much basic tools, but can be useful. The middle group are more advanced tools. These are either iOS or OS X tools that have been written specifically for the platform, or things like IDA Pro that are a little bit more advanced. I'll be talking about these on other slides, and this is pretty much what I use when I do reverse engineering. The last group are these comprehensive tool suites. There's been various companies that have kind of packaged all these tools together into a single suite that allows you to analyze apps pretty quickly. Now, there's conference talks pretty much on all of these. It's pretty complex, so we don't have time to go into all of them. But again, they're basically just packaged up with these other tools. So if you understand the other tools, it's really easy to kind of understand these tool suites. All right, so they're online tools, which is cool. But sometimes they're broken. For example, they won't run on iOS 7 or iOS 8. Or you might want to write your own tools. So the way to do this is to use iOS OpenDev. Now, back in the day, I guess a few years ago, this tool wasn't around. So if you wanted to write an application or a binary and then had it run on a jailbroken device, huge pain in the butt. You have to worry about code signing, entitlements, all this stuff, even if your device was jailbroken. iOS OpenDev does all this for you automatically. So what you do is you just download the installer and you install it on your OS X or your OS X box. And what it does is it sets up Xcode and OS X so that you can create binaries or applications that are run on a jailbroken device. So really nice, all you do is write some code, normally Objective-C or C, click compile, and then you copy it over to your jailbroken device. You just SCP it over or something, and it will run. iOS OpenDev is taking care of all the code signing and entitlements. All right, so let's talk now about getting some apps. Obviously, you're going to want to get some apps to reverse engineer. Kind of hard to read the slide, but so yeah, you can do it manually, but this doesn't really scale that well. Plus, we're hackers, we like to do things programmatically. So I was like, all right, let's figure out what iTunes is doing, and then can I write a Python script that allows me to download apps from the App Store. So I started sniffing. This first request just has a username and password and the name of the app I wanted to get. So I was like, oh, this looks pretty good, not too complicated. I then went and sniffed a little further, and there started to be things like encrypted blobs of data, which I didn't really know what they were. So I decided to Google, there's this one called KBSync, and I was like, what is this parameter? It's just this blob of data. And I didn't find a lot of results, except for one, which was on this Russian forum. I always find interesting results on Russian forums. Basically, it was a guy asking for someone to reverse engineer this. And they said, I will pay $10,000 if someone figures out what this is. At that point, I'm like, the Russians are offering $10,000. Nah, this is way too complicated. So I kind of gave up. Well, at least with that part of the project. But I shouldn't say I gave up. I basically said, hey, iTunes can download apps for us. So can we just leverage iTunes? So if you think about how iTunes does it, what it basically does is you tell it an app that you're interested in, and it loads up this application info page that has a link, buy, download. You click that, and then iTunes takes care of everything else, downloads it for you, and the end result is you have this encrypted IPA file. So I said, hey, we should be able to automate this. It turns out you can do it pretty easily. So if you use AppleScript, which is a language I have like this love-hate relationship with, because it allows you to automate Apple things really easily, but it's horrible to debug and randomly breaks. But it does work. So what we're trying to do here is basically get the app. So 2 simple steps. We first tell iTunes to load the app's information page. This is just the thing that has the screenshots and the download button. So we can do that by just saying open location and then giving it the link to the app. You can get the link to the app from the website. You can scrape it from there. Pretty easy. Once you've told iTunes to open that, what you can do is you can enumerate all the UI elements in the window, almost like it's a web page. And then you can find the button that says download or buy, and then you can say click, which sends a click event to the button. And as far as iTunes is aware, this is a user doing it, so they take care of all the authentication, all the network comms, and in the result, you have an app. So in about 10 or 15 lines of AppleScript code, we just downloaded an app. And we didn't have to pay $10,000, so kind of awesome. All right, so we have this app. Problem is it's encrypted. So Apple encrypts their apps, mostly for DRM purposes. If I download and pay for an app, I shouldn't be able to give it to someone else and have that run. So it's just them protecting the stuff. But it turns out, we can crack this app. And we want to break the encryption and decrypt it, because if we want to do static analysis, load it up in IDA Pro, look at the disassembly, it's got to be decrypted, right? If we look at encrypted an application, it's going to make no sense. So the good news is, when you run an app on an iOS device, on your iPhone, it's going to decrypt, right? The operating system has to decrypt the binary in order to let it run. So we can exploit this in two different ways to get the decrypted app. So the first way that's commonly used is a debugger, like a GDB, basically run the binary and dump it. Or there are actually some Cydia apps, such as Clutch, that do this automatically. And they both do the same thing. They basically wait until the operating system has run the app, until the app is running, and then they just dump the decrypted memory. Now it's important to know that this is a memory image. So you're not going to be able to run that decrypted app, but for static analysis purposes, good enough. All right, so you might want a more customized solution. So I want to talk about how you can strip off the encryption manually. You might not want to use GDB because it's a pain to automate, or Cydia apps are closed source and sketchy. So sometimes you might want to do it yourself. So here's a little DIY how we can remove the encryption from Apple binaries. So the first thing we need to do is get into the address space of the app that's running on the jailbroken device. Again, once we're in there, what we can do is find the encrypted memory and dump it to disk. So it turns out it's actually pretty easy to get yourself loaded into an application. If you use the DYLD insert library environment variable and set it to your decryptor library, when the application is executed, iOS will happily load that dynamic library into the address space. Now, once you're loaded, your dynamic library can scan the memory space, find the decrypted application, and just dump it to disk. End result is you now have this decrypted binary and you can statically analyze it. All right, so now I want to talk a little bit about some iOS-specific reverse engineering techniques. So let's start with some static analysis. The first thing I do when I get an app is I like to triage it. I like to say, after I've decrypted it, I'm like, what does it look like? What is its layout? Just kind of get a good overview sense of it. So I use OTool for this, which is an Apple tool that can dump a lot of information about the application. So if you use it with a -F or -H flag, it will show you the headers of the binary. If you use it with the lowercase l command, it'll show you all the load commands. Again, these are tell the loader how to lay out the binary in memory. The -uppercase L command is actually really useful. This will show you all the frameworks and libraries that this application imports. So you can see things like, is it using MacKit? Is it using SQLite? Other third-party libraries that might be interesting. And then finally, if you use the -O tool, what it does is it shows the class names and method signatures of the app. So class stuff is kind of like OTool-O on steroids. So remember that Objective-C invokes methods by passing messages. So to make this work, so in order for this to function at runtime, the Objective-C binary has to contain a lot of what I call runtime type information, which includes the name of the class, name of the method, and even names of instance variables. So this is really great from a reverse engineering point of view, because we have all this information that's in this binary. If you try to reverse engineer a C binary, normally this stuff is all stripped out. So if you run class dump, it'll basically dump all this information. So you can see it's almost like this complete rebuild of the class, including the instance method names, the parameters, like this. This is really helpful because you can then read these and basically look for functions of interest. So for example, again, we're looking at a banking app, we can see there's some authentication functions. A lot of times these might be done incorrectly or improperly. So this allows you to kind of drill down and find areas of interest really quickly. So IDAPRO, I'm sure you guys are familiar with it. It's kind of a de facto reverse engineering tool. So this slide gets into some disassembly. I won't spend too much time in it, but basically, little line of code at the top, we're generating a string. When we compile this, this is going to break down into two calls to obfc message send. So let's see if we can read this. Okay, cool. So the first line we're going to look at is the first call to obfc message send. So right here you can see a BLX R9 which says obfc send message. Basically what we do is we look back into this assembly because we want to figure out what is the name of the object that is getting this message and what is the name of this message. With that, those two pieces of information, we can figure out what this assembly is doing. So if we look back, we can see in R0, which is the first argument, we can see it's invoking NSDate, which makes sense because we're calling NSDate date method. If we look back in R1, which is the second parameter, this is the name of the method or the function we're calling, we can see that it's this date. So now we know this BLX R9 is calling NSDate's object, and the method it's invoking is date, which just gives you the current date. And then the result of this function is stored in R0, which is important because the next snippet of code is formatting the state object into a string. So again, we start at the BLX R9. R9 is obfc message send. We look back into this assembly. We can see this time it's the NSString object, and we're passing it the string with format method. And the parameters for this is going to be the time and then this loaded date, which is in R0. So this is, if you want to look at disassembly, you can figure out what's going on. But you know, it's really painful. I don't like to look at disassembly unless it's like a last stage effort. Yes, you will get a really good understanding of exactly what's going on, but it's very time consuming. So I like to do dynamic analysis because in my opinion, dynamic analysis is faster, it's simpler, and a lot of times gives you tons of insight into an app and allows you to find a lot of vulnerabilities really easy. So I'm going to be talking now about some types of dynamic analysis. We're going to talk about network analysis, file system I/O, debugging, and then code instrumentation. So network analysis, I'm sure you guys know what it is, conceptually, pretty simple. Basically, you want to sniff the network traffic to see what's going on. So when you execute the app, it goes through a proxy, it allows you to examine the network traffic as it's going off to the cloud. So on iOS, there's two steps to do this. First, you need a proxy. I use Burp. It's free, really easy to set up. It is written in Java, but I guess that's my only complaint. Say that's all Java in the box. So once you have a proxy set up, you need to tell the device to use the proxy. So there's two steps here. If you're going to be looking at SSL traffic, you have to make sure that the proxy can decrypt that traffic, otherwise you don't really see much. So in order for it to do that, you have to install the proxy's certificate on the device so that it's a trustworthy certificate. Apple makes this pretty easy. You basically email yourself, and when you open the email on the iOS device, iOS will say, hey, this is a certificate. So you can actually click it, and then it'll pop up and say install. And you click next, allow, and then you've got the certificate installed. Then all you have to do is go into the Wi-Fi settings for the device and put in the IP address and the port of the proxy server. Now, pretty much all application traffic will go to your proxy and allow you to see what's going on. So file I/O is another dynamic analysis technique. Again, pretty conceptually simple. You basically just want to watch what the app is doing in terms of reading and writing from the file system. So practically, how is this done? I use a tool called FileMon. It's conceptually exactly the same as the Windows FileMon tool. It basically shows you what files the application is creating and then what it's reading to or writing from. The only problem is there was a bug on iOS 7, but again, since I use iOS OpenDev, I could patch this tool and very easily just recompile it and then it ran on my device. So this is a great example of, even though there's a tool out there, it's open source, it's awesome. If it's broken, sometimes you have to fix it or basically port it to newer versions of iOS. So another dynamic analysis technique is debugging. Again, this isn't specific to iOS. Conceptually, again, pretty simple. You basically want to run the app under a debugger, and then you can single step through, set breakpoints, look at memory, poke around. So for debugging apps on iOS devices, you use GDB. So GDB is the de facto debugger. I think it's the only one that works, actually. So these are just some tips and tricks, some iOS-specific things. I found it's actually easier to wait for the app as opposed to running it directly under, running the app directly under the debugger. A lot of times apps either have anti-debugging logic or GDB crashes. So use the wait for command and put the PID and the app name, and then when you start the app, GDB will automatically attach to it and you'll be good to go. Another command is good is the info shared command. This will tell you all the libraries or modules that the app has loaded. So again, really useful, tells you kind of what the app is doing. The H flag allows you to change the thumb mode. So sometimes if the application is using thumb or thumb2, GDB gets confused and starts encoding it in ARM, even though it's encoded in a different way. So you have to tell it to switch, and then once you do it, decodes it correctly. And the last one is the PO, which stands for print object command. And this is a really powerful command that I use all the time. Basically, it's smart enough to figure out if something is an Objective-C object. It can parse it and display all its contents. So normally if you have a list or a dictionary and you don't give it the PO command and you just try to dump that memory, it's just going to be a random number of bytes. It might have metadata, the dictionary, stuff like that. But if you use the PO command, it's like, oh, I know this is a dictionary, and I'll nicely print out all the objects in it in this like nice tree format. So it's a very powerful technique. All right, then the last dynamic analysis technique is app instrumentation. Conceptually, it's pretty simple. Basically, what we're going to do is we're going to inject code directly into the application. And then this allows us to do a whole bunch of cool things. We can bypass any client-side logic. We can execute any code within the application, even if it's hidden code. And then most powerfully, we can manipulate the app runtime. So we do this with a tool called script. That's how the author says should be pronounced. You download the package, and then you install it, and then you give it the PID of an application that you want to target. That's all you have to do, and once you do that and hit enter, it gives you this nice little prompt, and this is almost like a remote shell into the app's address space. So here we're enumerating the UI components. This is kind of like dumping the DOM tree for a web page, if you use like the developer tools in Chrome. You can also run any commands, invoke methods, poke around, really powerful technique. So here's a simple example of that. This is the Bank of Hawaii app. See, I'm poor, I'm a security researcher, not a lot of money. So I wanted to become rich. So what I did was I patched to this app using script. And then in memory, I found the text field, the UI text field. And I invoked that command. The number at the top is just the address of the text field. You can get that by enumerating the tree of all the UI elements. And then I invoked the .text method and gave it a new number. And then that changed my bank account. Unfortunately, this is just at the UI level. But this just shows you can manipulate the app in any way. So if there's client-side logic, like there's an authentication prompt that's popping up there, you can hide that window. You can change that window. You can change text fields, stuff like that. So it's a really powerful way to kind of poke around, play with the app in maybe ways that it might not expect. All right, so now let's talk about some real bugs in iOS apps. I want to give some practical examples and show you what to look for and what you might find while looking at while reverse engineering. So it's important to kind of have this what I call mobile mindset. We're not talking about remotely exploiting or implanting mobile phones. It's more about getting access to this data. Again, remember what's on your phone. It's your emails, your pictures, your current location, all this stuff. So attackers have a myriad of ways to get this. Your phone is lost or stolen. They sniff the network, your backups, if they get you to install a shady app. So the most common class of iOS vulnerabilities, I think, are network communications. This is kind of sad because, network comms, it's kind of, we have ways to secure it, right? There's standard network security practices. First one being, if you're transmitting sensitive information, use SSL, right? This isn't that complicated. And do it correctly, so don't allow self-censorship. Secondly, if content is rendered on an app and is coming from another user or from a website that's out of your control, the app should sanitize this to prevent things like cross-site scripting vulnerabilities. So again, I mentioned these are standard network practices, so it's kind of sad to see so many mobile applications just getting this completely wrong. So the first thing I always do is check, does the app use SSL, which is transferring sensitive data, and does it do it correctly? So Apple actually makes it really easy to use SSL. All you have to do is put HTTPS at the beginning of the URL. And Apple takes care of all the cert validation, generating, everything. So really easy to do right. The problem is that developers can, and sometimes do, override this to allow self-signed certificates. Now I'm guessing they mostly do this for testing reasons, but a lot of times this makes it into production code. And as I'm sure you guys know, if you allow self-signed certificates, you're going to be vulnerable to a man-in-the-middle attack. So to spot this bug in code, there are several ways to do this. First, you can look for the call to set allows any HTTPS certificate. This is a method call that you can invoke on iOS, and then from here on, you can accept self-signed certificates. You can also implement this category, which is will send request for authentication challenge that iOS will call when it's validating a cert, and you can say, yeah, I'm okay allowing this self-signed certificate. So if you see either of these two, the app is probably vulnerable to man-in-the-middle attack. So here's some disassembly from an app that allows a self-signed certificate. We can see it's invoking, well, first here's our friend obj message send. We look back into disassembly. we can see it's invoking the set allows any HTTP certificate. So when the app makes this call at runtime, it's telling the iOS, I'm cool with accepting the self-signed certificates. Again, at this point, it's vulnerable to man-in-the-middle attacks. Again, I find it way easier just to look at the network traffic and do dynamic analysis. I really try to stay away from disassembly if I can. It's just painful. So dynamic analysis makes it a lot easier, and you can kind of see all the network traffic that's going across. You can see if it's using a self-signed certificate. You can also find things called mixed content attacks. So mixed content attacks is where you have a secure web page, for example, a banking website, but then they're using where there are some HTTP requests, maybe they're going out to a third site to load some other content. The problem is the attacker can manipulate this HTTP content. So here's an example. The Bank of Hawaii app does exactly this. The majority of its communications are all SSL, which is good, but it does go out and load a certain JavaScript from websites and does that via an HTTP request. So if you're an attacker on a local network, sitting at Starbucks and someone's checking their bank, you can see that request go by, and since that component is not protected by SSL, you can manipulate it with consequences. So that's exactly what I did. What I did was I injected some JavaScript into it, and basically it's a malicious pop-up that says, hey, your session has expired, and then I inject a malicious login prompt. And the idea is the user would be like, oh, my session has expired. Click OK, put in their password, click login, and then that information goes to me as the attacker instead of the bank. Now, if your PC did this, on your browser, you might be a little skeptical of what's going on. But the problem is there's not as many visual clues in applications. So, if I saw my banking app say my session expired, I probably wouldn't think twice of it if it was on my phone. Whereas if it was on my PC, it would be problematic. So, mobile vulnerabilities can exacerbate or make vulnerabilities worse. So this is another network issue that we found. And this is a problem because this application did not pin its certificates. So Dropcam is a very popular Wi-Fi monitoring device. It's now owned by Nest, which is owned by Google. The problem is their app doesn't pin SSL certs. So SSL pinning is an extra layer of security. Basically what it says is that I will only talk to a well-defined set of servers. So I don't care if you give me a signed certificate, if it's not to the server I'm expecting, I'm not going to talk to it. So if an application doesn't pin its certs, it can be vulnerable to a man-in-the-middle attack if the attacker has a compromised CA, which may be the case if it's a government, or if it can convince the user to install a certificate on their device. And this isn't that far-fetched. A hacker could socially engineer a user to do that. Send them an email saying, hey, welcome to a new company. This is the IT department. Please install the certificate. And again, iOS will recognize that in an email, and if you click it, it'll say, do you want to install this? And if you click yes, at this point on, the application can be man-in-the-middle. So let's man-in-the-middle Dropcam. So here's a burp capture. Again, this is the proxy showing the username and password. Now, this is exacerbated because Dropcam does not use dual-factor authentication. Also, it does not have any shared session alerts. So if you man-in-the-middle the attack, the app once and get the username and password, as long as they don't reset their password, you can persistently and surreptitiously access their account at any time. And again, this is a device they'll have sitting in their house that's watching what's going on, so you can easily spy what's going on. For example, Edward Snowden is talking to his girlfriend. That's really his girlfriend. So another problem that these apps have is they're also open to common web vulnerabilities. Mobile apps a lot of times will render content in what is called UI web views. And if they don't sanitize the input, they can be vulnerable to cross-site scripting attacks, just like the website. So this is an older version of Skype on the left here. You can see that it was vulnerable to a cross-site scripting vulnerability. And the payload for the specific attack actually exfiltrated the user's entire content because the Skype app had to talk to their address book, so the cross-site scripting payload could access that as well. You also see a lot of server-side APIs. A lot of times mobile apps will talk to undocumented or private API functions. You sniff that in network traffic and see what's going on. You can a lot of times query these APIs directly yourself and gain access to a whole bunch of stuff. So Snapchat is vulnerable to this, or you can access people's phone numbers and whatnot. All right, so the next common category of iOS bugs deals with data security. So first I want to talk about how to secure your data and why it's even necessary. So When you power off your iPhone, iOS automatically encrypts everything, which is good. So at rest, it's encrypted. The problem is when you boot the device, it automatically decrypts everything before you get to the password prompt, unless you use the data protection API. So Apple provides this extra layer of encryption called the data protection API. Basically, it encrypts things with a key that's derived from your passcode, which makes it more secure. So the problem is, though, the developers have to opt into this. So if they don't, and the attacker can boot the device, then they can access whatever data is there. To figure out what file permissions, and I'll talk about this a little more later, you can use this tool called FileDP, and that will show you if the file is protected with a secondary layer of encryption. All right, so I mentioned Apple does provide a pretty easy way to secure this data, but the problem is people have to opt into it. So we all know developers are lazy. I do some developing, so I can say that. So we see a lot of apps that are vulnerable to data storage issues, basically where sensitive data is not encrypted. So we see them storing this within the binary, within property lists, within databases, or even log files. And I'll give examples and kind of go through each of these. So sometimes developers hard code sensitive information into source code. And then obviously when they compile, this sensitive information makes it into the binary. So this is an example. It's an app called PuffChat, which is kind of, it's a texting alternative to Snapchat. So basically you can send self-destructing texts. The CEO said, quote, "It's great for confidentiality and discrete messages you want to have permanently erased." So you're like, oh, this sounds cool, security app. It's going to be secure, right? Well, it turns out that it was a secret API key that was embedded in the binary. So if you decrypt the app and looked at this in IDA Pro, or just sniffed the network traffic, you would see this static key being sent to the API. Well, it turned out this key allowed any operation on the APIs on any account without any other authentication. So you find this key, you can basically query any other user's account, read their text messages, read them. So there's a quote from the guy who found this, which is true. You know, you can't put a secrets in binaries, reverse engineers are going to find it, but like here they didn't even try. And again, to me, this illustrates that you have this secure application, but if you reverse engineer it, there's just blatant vulnerabilities that completely undermine all the security. All right, so now let's talk about storage within a plist. So plists are just property lists, XML lists, and the most common one that is abused is the user defaults. So the user defaults is a capability that iOS exposes that allows developers to store user preferences. It's really convenient to use. You don't have to worry about opening files, file I/O, closing file handles. The example right here, you can see we just set a default and then later we retrieve it. So the problem is, since it's so convenient, people put all sorts of sensitive information like passwords and session IDs in here, which is problematic because this file is not protected with the data protection API. So this means if this phone is lost or stolen, and the attacker can boot the phone and gain access to the file system, which they generally can, this means that any information that's stored within here is going to be in the clear, unencrypted. So here's an example of this. You look at the disassembly on the left, you can see that it's invoking the NS user's default. And again, disassembly, not a big fan of. So what you can do is you can just go and actually look at the file and see what's there. So this is an example of an app that was in the App Store that dealt with user medical records. So again, you would be like, all right, this guy's probably secure. Well, it turned out that they were storing the session ID in this unencrypted plaintext file. So what this meant is that if the user ever lost their phone, the attacker could access their account and all their medical records without their username and password. And I was actually able to take this file, put it, copy it off the device, put it on another device, and it automatically logged in because I had my session ID. Yes?
If the phone's like using encryption for the full disk encryption, then this is encrypted or then also?
So it is when it's powered off, but when you power it on, iOS will automatically decrypt everything so that it's available to applications, unless they use that second layer, the data protection API, which means the files are decrypted until the user puts in their passcode.
But that's other applications on the phone. When like someone who stole your phone connects it to his computer, his or her computer, would that work or?
So it depends again. If they're using the second layer of encryption, they would have to put They would have to know the user's passcode.
Yeah, but if they're not using but the full disk encryption is on, they just connect to another Mac.
Yes, it'll be booted, they'll be able to, well, they have to jailbreak the phone or access it in some way, but that's pretty trivial to do. But end result is they don't need the user's passcode. So it's pretty easy to do that. So in this case, yes, if you could boot the phone and access it, plug it into iTunes and jailbreak it or something, then you could see this information in the clear. So again, since this was a medical application, I think this is a HIPAA violation. Again, this was published in the App Store. So kind of scary what makes it in there. So a lot of apps use databases, which is fine. If they're using this data protection API, this means that if the phone is lost or stolen, the attacker would have to know the passcode. Problem is, a lot of apps do not use this. Here's an example of WhatsApp. There's a public write-up about this, but we also found this when CINAC was doing an audit. And we noticed that I used FileOn to see what files the database was writing, what files the application was writing. And there was this one called chatstorage.sqlite. I used the file VP tool to say, hey, is this file encrypted or not? I said no, which is cool. And then I went and dumped this, and I could see my chat messages in the clear. Again, this is problematic. If the user's phone is stolen, everyone can see your chats, which may or may not be a good thing. Another example is storage within a log file. And I should put storage in quotes here because a lot of apps don't willingly store things in a log file. They just write debug and error messages. But this is problematic, if they're writing sensitive things. Again, you can look at the disassembly, or you can just use FileOn to see if it's writing to a log file, and then go look at that file to see if there's any sensitive information in there. So here's another example of an app that CINAC audited. In this case, it was logging its HTTPS requests to the server. So here we can see in the clear the CRSF and session ID tokens. Again, so this phone was lost and stolen. You can access this and automatically log into the user's account without needing their username and passwords. Geolocation is a really cool feature. It shows you what's nearby, all that fun stuff. But the problem is, it should be secure because it's showing you your current location. And knowing someone's current location and where they are can reveal a ton of information about who their family is, what their political preferences are, where they work, where they live, where they travel. I mean, you can really build a really good, overview of what the person's doing. So there's a few issues. One is on iOS, if you don't specify a level of accuracy, iOS defaults to the highest level of accuracy, which is down to the foot or inch level accuracy. This is problematic because then if the app does not secure this information, either it writes to the file system unencrypted or it transmits it to a server not using HTTPS, or if the server API doesn't respect authentication requests, you basically now leak the user's exact location, which can be problematic. So the best way to do this is just use file IO to see what it's writing, or sniff the network to see if GPS coordinates are going across the wire. So my coworker Colby talked yesterday about Grindr. And Grindr is basically an app that's used by gay men for dating and meeting up. The talk was great because basically Grindr does like everything wrong you could do. So it used precise relative distance. Didn't do any error rounding. It allowed you to spoof your location, and all the data that was sent to the APIs on the back end, you as an anonymous user could query, and it would just give you this huge dump of user information. So because you could spoof your location, what you could do is you could say, hey, I'm in location A, B, and then C, and then even though it was only giving you relative distances of users nearby, you could do a trilateration attack and then find the exact absolute location of users. So here you can see a map from San Francisco. Obviously there's a lot of gay people there. We reported this to Grindr early in the year. They basically told us to shove it. They said, hey, this is what our app does. And we were like, well, you can track anybody, anywhere in the world at any time. That's down to their exact location. And then fortunately later in the year, it was reported that the Egyptian police were using Grindr to track down gay people because it's illegal to be gay in Egypt. So Grindr then did implement some geofencing, but again, only in Egypt. So in the US, you can still track anybody, anytime. Kind of scary. Reverse engineering can also show if an app is just being shady. Again, this is a geolocation problem. Whisper is an app that allows people to send anonymous secrets. It's kind of like a secret app. The problem is, even if you as a user said, don't share my setting, don't share my location, it would still send that to the server. It wouldn't propagate that out to other users, but it was still sent to the backend. The problem was that, according to The Guardian, this information was then saved indefinitely and then given over to the US Department of Defense. So again, with reverse engineering, you could be like, hey, why is it sending my location to the server? I said not to share it. So here's a map. This is actually from the report from The Guardian, the newspaper, and it's the National Security Agency. And you can see there's all these people whispering or sharing secrets. So I don't know. I think this is one case where I'm okay if they shared that information with. But in general, if an app you think is secure and you say don't share my location, it probably should. All right. So we talked about some general categories due to time constraints. We can't go into all these other places, but there are other places to look for bugs in applications. A lot of apps will use binary cookies. They kind of like session IDs. These aren't stored encrypted, so if it's caching stuff, a lot of times you can look at these binary cookies and then access users' accounts without credentials. If the app is caching requests and an attacker can inject a 301 HTTP redirect request, a lot of times they can continually redirect the app. Apps also might use IPC mechanisms, for example, special URLs. For example, Skype exposed one of these. It had a vulnerability where it didn't validate where this was coming from, so web pages or other apps could automatically make background Skype calls to premium numbers without the user being authenticated. And then the last one is screenshots. So when you press the home button, the iOS will take a screenshot as part of the animation to hide or minimize the app. So obviously, if you're typing something sensitive, you probably don't want this to be screenshotted because those screenshots are not encrypted. So applications can register a callback that says, call me when someone presses that button so I can wipe out or hide any sensitive information. So apps should be doing that. So it's always a good place to check those screenshots to see what apps are not doing that. All right, so hopefully I showed you that there's a lot of insecure apps out there. Hopefully though, using the techniques we presented here, you guys will be able to reverse engineer apps and find some bugs, and hopefully make the App Store in the iOS world safer. And also, if you sign up with Synac, we have a lot of customers that have mobile apps that are very buggy, so you can get paid as well. So you're making the world a better place and getting paid. It's like win-win. Awesome, so that is a wrap. Thank you guys for listening to me ramble. Do you have any questions? And also, you can download the slides. They're on SlideShare. Dig into them and look at them some more. Questions? Cool. Also follow me on Twitter. So I think it's lunchtime now, so thanks for putting in the full hour. So we do have some tools to automate some of the